It's record. Oh, yeah. No, started transcription. What is transcription? Wait. Is it recording or not? No, I think it is recording. Yeah.
You can stop the transcription.
Where is transcription?
In those three dots, if you click, you will see stop transcription.
Oh, what does it mean?
I think I mean, whatever you say also gets. And if you open the chat, you will see all the words like captions, closed captions.
It is recording now. Yeah, it is recording.
Okay,
yeah,
let's start.
Yeah, maybe we can start. I think. Welcome to the second lecture by Munna Naik. So I think he can start. Munna.
Okay.
Yeah, you will.
Welcome to the second lecture. So
yeah.
Today I will say some things which will be familiar to most of you. Okay. So recall from the previous lecture. Actually, I have defined something called matrix Lie group. Okay. But from the previous lecture, it seems that I need to define that the notion of Lie algebra and the notion of Lie group. Okay, so and sooner or later I will need these two concepts. So it is better to define now. Actually, if you have seen my notes, actually I have added the definition of Lie algebra there. Just writing, and this is the definition. Let V be a vector space over K, where K is R or C. Is called a Lie algebra over K if there exists a bilinear map from V cross V to V such that, and this bilinear map is called Lie bracket. Okay, so that it satisfies two properties. First thing is this Lie bracket of x and x is equal to 0. This is called anti-commutative. Okay. Second thing, and it has an equivalent characterization. Lie bracket of x and y is equal to minus of Lie bracket of yx. And second thing is something called Jacobi identity. What you take Lie bracket of x and with Lie bracket of y and z. So and you cyclically permute that, and that will add up to 0. This is called Jacobi identity. This is called Lie bracket. So you take examples. Let V be any vector space over K, where K is either R or C. V can be thought of as a Lie algebra with Lie bracket 0. Okay, so this is the thing. And second example, okay, you can take MNR or MNC. You can take let A comma B belongs to B. You can define Lie bracket of AB is equal to AB minus BA. So it can be checked that with Lie bracket defined above, B becomes a Lie algebra. So this is a definition of Lie algebra. Now I have also given the definition of Lie group. So okay. Definition of Lie group is something I have given. So let me write that once more. Let G be a group and G and a smooth manifold and a C infinity manifold. Okay. G is called a Lie group. If first condition this x y going to this x dot y is smooth G cross G to G. Second thing is x going to x inverse is smooth from G to G. Okay. So if you want to say these two conditions with one stroke, then this is precisely the definition which I have given in the previous lecture. That is xy going to xy inverse is smooth from G cross G to G. Okay. So definition examples of Lie group. examples. This is Rn with addition. Okay. The Cn addition. Then you can take this H1. This is this is a unit circle. This is with multiplication, and this t to the power n. This is S1 cross S1 n times. This is product wise multiplication. GLNC and GLNR. These are some standard example of Lie. Okay. Now, okay, so now there is a theorem that if you denote this TEG, this is tangent space at the identity. Then you can give a Lie algebra structure here. Structure here. Yeah, and this is called actually Lie algebra also. So I did so TEG and with this Lie algebra structure. Called Lie algebra of group of Lie group G. And it is usually denoted by this German Gothic G. Okay. So now the thing is, there is a theorem due to Cartan. Theorem due to Cartan. Say that let G be a Lie group and H be a closed subgroup of G. Then H has a H becomes a Lie group. It's
Muna, what is the list structure you took on T, the tangent space at identity?
yeah, I have to really just you assume that this has a Lie algebra structure.
Okay. Okay.
You sort of take the actually you take C. The thing is, okay, I will explain this. Okay.
I think you can write that in one line probably.
No, I will can write that, but okay. G has a then G becomes a Lie group. Okay, this theorem is due to Cartan. Okay, so what I will do that you take X belongs to some TEG. Okay, so you define this XG. Okay, this X is a belongs to TEG. So you define DLG of XE. Okay, LG is the derivative of this translation, this map. LG of H is GH. Okay. Now this XG becomes a vector field. Becomes a left invariant vector field. So you can actually define. You can take this vector y. Okay. So this actually this is dependent of G going to XG. This is a map you are getting here, where XG belongs to TG of G. Is it clear? What I'm saying that you take X belongs to TEG. Okay, so you take Now you define xg is equal to dlg of
No,
x.
what is this notation? Xg is equal to DLG at the point E
Yeah, this
of
is
XE. Okay.
xe. See, the thing is, if you take a element in the tangential identity at G, then you need to define a left invariant vector field. Okay, and how that left invariant vector field is defined? Xg is DLG at E, and after this is applied on Xe, where X is equal to X. Okay, just just leave this thing now. Actually, I do not need this thing now. But what I am saying is correct. Okay. So. See, the thing is,
maybe Munna, you can also define what are drift invariant vector fields, right?
okay,
Yeah.
actually here I do not know need this now. So whenever there will be need, I will define this. Okay. So just you assume that this has a Lie algebra structure. Okay. Okay. So just for the time being, you just forget this thing. Okay. So the thing is, I have seen that G be a Lie group and H be a closed subgroup of G, then H becomes a Lie group. Okay. So that means, and I have seen that we have seen that GLNC is Lie group, and any let G be a matrix Lie group. Okay, so that means G is a closed subgroup of GLNC. Therefore, this implies G is a Lie group. Okay, what is the tangent space at G? G is equal to, I have defined that this is nothing but, in this case, this is x belongs to MNC, so that e to the power tx belongs to the group G for all t below to R. Okay, so from the here actually I have given that exercise that to show that small GLNC is 0 nothing but MNC, and GLNR is equal to MNR. Okay, so this is SLNC trace of x is 0. Okay, so now small son is x belongs to MNC, so that MNR x plus x transpose 0. Okay, so now you can take this exercise. By using Lie theory, you can say that this is actually a Lie algebra. But what the exercise is, you show that directly, okay, directly verify without using Lie theory that these are basically Lie algebras. Yes. Without using verify that sets above are Lie algebras, and
So what are the meaning of this? Like we using
this
Lie theory and directly?
directly this you should take this set. Suppose SLNC. Okay. So this is the set x belongs to MNC. So that trace of x is 0. Okay, so let B be this set. Okay, so that B is Lie algebra. And what is the Lie bracket here? This A belongs to B, B belongs to B. The Lie bracket is nothing but AB minus BA. This is in fact trivial exercises. Is it clear?
Yeah.
Okay,
So this is directly, right?
Directly. Just directly verify the Jacobi identity, whatever the things. Actually, you have to just show this thing. If A belongs to B, B belongs to B, this AB belongs to B. That's all you have to show.
And what is the thing like using Lie theory that you show that this is the tangent space at identity?
You have this, the thing is, this tangent space become a Lie algebra. Okay. So you identify that tangent space of GLNC with MNC, then in the abstract setting, this is also definition of Lie algebra. Okay, so from there actually, first you in the abstract setting you show that this is the Lie algebra, if it, and then actually you conclude here for the group MNC, for the group any matrix Lie group. Okay, this is something you have to really know a little bit of Lie theory. So that is okay. So that is all about Lie algebra. What I am saying. So as I said that we are interested in learning this so-called classical Lie groups, and we are interested in basically the finding this topological properties of Lie groups. Mainly this compactness, connectedness, everything. And you will see that this connectedness, number of connected components of this classical Lie group is equal to number of connected components of this so-called maximal compact subgroup. And fundamental group of this classical Lie group is equal to the fundamental group of this maximal compact subgroup. So for that reason, we need to really prove some topological properties of this compact Lie group and maximal compact Lie group, maximal compact group, and you will see that these are nothing but SON, UN, or SPN. Okay, so for that reason, we first really prove some topological properties of these compact groups. So first proposition is very clear that this UN, SON, ON, this SON, these are compact. This is clear. Okay. I will not prove it. Connectedness. Position is UN is connected and SUN is connected. Okay. So proof is also simple. Let me. I will give this proof actually. Proof. Let A belongs first one. Let A belongs to UN. This there is a spectral theorem by normal operator that any normal matrix is unitarily diagonalizable, and unitary matrices are unitarily diagonalizable. So there exists U belongs to UN, so that A is equal to UD in U inverse, where D diagonal. Okay. Now see, A is similar to D, so therefore eigenvalues of A and eigenvalues of D are same, but eigenvalues of D are nothing but diagonal elements of A. So D is of the form e to the power I theta 1, 0, e to the power I theta 2, 0, 0, e to the power I theta n. So the thing is theta 1, theta 2, tan belongs to R. Okay, this is clear. Now I will use a notation that this will be diagonal of e to the power I theta 1, theta 2, e to the power I theta n. That means it has diagonal elements e to the power I theta 1, e to the power I theta 2, I theta n, and rest are 0. Now I take this dt. This is same thing as e to the power it theta 1, e to the power it theta 2, e to the power I theta n, and rest are 0. So now observe that d0 is equal to identity and d1 is equal to your what d. Okay. Now take gamma t is equal to a, sorry, gamma t is equal to u dt u inverse. Okay. If you put this gamma 0, this is called u gamma 0 u inverse, then that will be identity. Okay, what is gamma 1? Okay, actually some people complain that I scroll very quickly. If I am scrolling very quickly, then just let me know. So gamma 0 is equal to identity. So this gamma 1 is equal to u d1 u inverse, and u d1 is equal to a d u inverse. This is equal to a, because u d u inverse is equal to a. So gamma t between 0 and 1 is a path joining identity and a, so un is path connected. So now you can apply the same argument for exactly sun. Suppose, but you have to take. So let's suppose let a belongs to sun. Then there exists u belongs to un. So that a is equal to u d u inverse. Okay. So where d is equal to e to the power I theta 1, I theta 2, e to the power I theta n, and the rest are 0. But since a is belongs to sun, this determinant of b, this is determinant of a is equal to 1. Okay. So I will get here e to the power I theta 1, e to the power I theta 2 into e to the power I theta n is equal to 1. So I will get e to the power I theta n, e to the power minus I theta 1 theta 2 plus theta n minus 1. Okay. So I will replace this theta n by okay. So what I am getting, b I am getting, this is nothing but diagonal of e to the power I theta 1, I theta 2, e to the power I theta n. Okay, so this is I am replacing the e to the power theta 1, e to the theta 2, e to the power minus I theta 1 plus theta 2 plus theta n minus 1. Okay, now you take dt diagonal of e to the power I t theta 1, now e to the power I t theta 2, e to the power minus I t theta 1 plus theta 2 plus theta n minus 1. Okay. Now if you take exactly the same argument, this gamma t is equal to u dt d inverse. Okay, so this will be belongs to, actually this not actually this will be belongs to sun. So gamma t is a path joining. You can complete the proof. Okay, joining I and a. Okay, so this proves the fact that sun is path connected. So here actually you write this thing. Here actually I missed something. Gamma t, you have to show that this belongs to UN. This is easy. Okay, so this proves the fact that UN is path connected and SUN is path connected. Now I want to show that SON is also path connected. For that, actually, we need this thing, something called normal form of orthogonal matrix, special orthogonal matrix. Okay. So suppose let theta belongs to R. I define this rotation matrix R theta is equal to cos theta sin theta minus sin theta cos theta. Okay. Now check that R0 is equal to identity. This and this is a 2 cross 2 rotation matrix. So determinant of R theta is equal to 1. R theta belongs to SO2. Okay. Now there is a proposition. So okay, proposition let A belongs to SO2. Okay, so then there exists a SO2n. Suppose A belongs to SON where n is given, then A belongs to SO2n. Then there exists a matrix Q belongs to orthogonal matrix O2n, so that A is similar to some matrix R. A is equal to Q transpose RQ. Okay. Where R is of the form R theta 1, R theta 2, R theta n. Okay, rest are 0. This theta 1, theta 2, theta n belongs to. Okay, so this is for even case. For odd case, there is a similar thing. Let A belongs to SO2n plus 1. Then there is just Q belongs to O2n plus 1. So that A is equal to Q transpose RQ, where R is of the form, it will be R theta 1, R theta 2, and R theta n. Okay, so let us write it case please. Okay. This R is equal to, you took R theta 1, R theta 2, R theta n, and last entry is 1, and the rest are 0. Okay. This 2 cross 2 diagonal matrix, so these are 2m entries, these are 2m entries, and this is 1. Okay, so theta 1, theta 2, theta m. Okay. This is not difficult to prove, and proof you can try yourself. Proof, try yourself, or see Halmos or Horn-Orgenson. You can see any of this book, but I suggest that you see Halmos. Okay. Now this is called the normal form of
Almost which book, Muna?
matrix. Vector space.
Name of the book is Vector Space.
You better you try yourself. Okay, this is not a very difficult thing that you can do it. Just you have to use this normal matrices are unitarily diagonalizable. Then you separate the real part, imaginary part, and see that since the matrix is belongs to SON, then the some rotation matrix will come, and you have to arrange those bases. So this is the thing. So let us see that what I get. So let A is a SO2M, then there is Q belongs to O2M. So that A is equal to Q transpose RQ, where R is R theta 1, R theta 2, theta m in the block, and the rest are 0. And similarly, let A belongs to SO2M plus 1, then there is just Q belongs to O2M plus 1, so that A is equal to Q transpose RQ, where R is of this block. Okay. Now, proposition. This is SON is connected. Second thing is ON has two connected components. Namely, okay, SON and ON minus, where ON minus is something like A belongs to ON, so the determinant of A is minus 1. Okay. So first thing I have to prove that SON is connected, and second thing I have to prove that ON has two connected components, namely SON and ON minus, where ON minus is A belongs to ON, so the determinant of A is minus 1. So proof is very clear from the null. So let A belongs to SO2M. Okay, so by normal form, we can get Q belongs to O2M, so that A is equal to Q transpose RQ, where R is equal to R theta 1, R theta 2, R theta m. 0 theta A belongs to R. Now define same argument, RT is equal to RT theta 1, RT theta 2, RT theta m. This is 0. So R0 is equal to identity. So and R1 is equal to your R. This is by definition. So define gamma T Q transpose RT Q. You can check that this gamma T belongs to always SO2M. Okay. So now what gamma 0 is identity. Gamma 1 is equal to Q transpose R1 Q, Q transpose RQ. This is nothing but A. So gamma T okay, is a path joining identity and A. So that SO2 to M is path connected. By exactly similar, this is for even case. By this similar argument, you get that SO2M plus 1 is path connected. So this is clear. So I have proved that SON is path connected.
So where are you using exactly that it has determinant 1?
Where you are raising?
That it has determinant 1.
Because it has to lie inside SO2M. You have to construct a path in between in SO2M. If suppose RT has not determinant minus 1, then gamma T will have determinant minus 1. Then that will not be path inside SO2M.
Now to start with, like Q transpose RTQ. So since it is in SO2N, so like Q and Q also have determinant 1, right?
Q
Q will have
belongs to
determinant 1 or not?
orthogonal.
It is
No,
orthogonal only.
Q is orthogonal only, I'm saying. I do
No,
not
I'm
need
just
the.
trying to think that where will this proof fail if you start with an element A in O2M?
See this if A belongs to O2M,
Hmm.
then you will not get this form. You will get 1 minus 1 something like that. Okay, we have a form, but I don't want to do it.
Okay.
Okay. So what I'm saying that since you have asked this question, you take this A belongs to On minus, okay, determinant minus 1.
Hmm.
So write down the normal form,
Hmm.
normal form that matrix, and try to use that thing that to show that this On minus is path connected. Then you will see that there are some problems. Okay. So second thing is I have to prove that On has two connected components. So observe that determinant map this On to +1 and -1 map. This is not a is a continuous and not constant, non-constant. So you will get that On is disconnected. So number of connected components is greater than or equal to 2. Now I take this, let I tilde, this diagonal matrix where everything is 1 except this last entry, this something called -1. Okay, you will see that determinant of I tilde is equal to -1. Okay. And I tilde, this implies I tilde belongs to On minus. Okay. Observe On minus is nothing but I tilde into SON. Okay. Now, since since matrix multiplication is a continuous function, since SON is connected, so we get that On minus is connected because this is just multiplication by a matrix, fixed matrix I tilde. Okay, now I will get On is SON disjunct union of this On minus. Okay. So this is connected, this connected. So that will imply that number of connected component is less than or equal to 2. Okay, so I have shown that this number of connected components is greater than or equal to 2. Here I am saying that number of connected components less than or equal to 2. This implies this number of connected component is equal to 2. See, the thing is one thing from this thing, this line, you cannot really conclude that On has exactly two connected components. Okay, for instance, you take this real line, you take -infinitive 0, and this is disjoint union of 0 infinitive. This is connected, but you cannot conclude that R has exactly two connected components. You can always conclude that number of connected components is less than or equal to 2. This is important thing. Okay. So I have shown that On has two connected components. This is SON and ON minus. Usually people do this in homogeneous space way, and we will also do that one thing group for that SPN. So, but I really like this linear algebra approach. So now let us go to work to something important, some definition. Let A belongs to MNC. A is said to be positive definite. First, if A is Hermitian, this A is equal to A star. Here A star definition is something like A bar transpose. Okay, this is called Hermitian. A is Hermitian. Okay, so for second thing is this inner product Az and Z is strictly greater than 0 for every zero not and Z belongs to C. Now, if A belongs to MNR, so then this condition, first condition will reduce that A is symmetric, A is positive definite. This if and only if A is equal to A transpose, this is symmetric. Second thing is B transpose AB is strictly greater than 0 for every 0 not to B belongs to R. Okay, this is something. Okay, so this is a very important matrix. So I denote some notation P and C. This is A belongs to M and C, so that A is positive definite. All complex positive definite matrix. This P and R, A belongs to M and R, so that A is positive definite. Okay. Now this is HN. This is A belongs to M and C, so that A is equal to A star, Hermitian matrix. These are Hermitian. Okay, so now this is Sn. This is A belongs to M and R, so that A is equal to A transpose. This is symmetric. Okay, so okay, so these are the notation we will use. As PNC is the complex positive definite matrix, PNR is the real positive definite matrix, HN is the set of all Hermitian matrix, SN is the set of all symmetric matrices. So now exercise this so that HN and SN are real vector spaces. These are real vector spaces, but they are not complex vector spaces. Okay, you actually I should write this as but HN is not a complex vector space. I should only write for symmetric. Okay. Now let okay, there are equivalent characterization of this so-called positive definite matrix. So this proposition you can prove this. This is X, and you can take it an exercise. Let A belongs to HN. Okay. So A is okay. So A belongs to P and C, means A is positive definite if and only if all eigenvalues of A are strictly positive. Okay, strictly positive. Now similarly, I can take two parts. Let A belongs to Sn, then A belongs to PNR if and only if all of A are strictly positive. Okay. Now this you can prove it is on your own. So now discussion. So let A belongs to say HL. So now A is a Hermitian matrix, and Hermitian matrix are normal matrix. So there exists U belongs to UN. So that okay. A is equal to U D U inverse, where D is diagonal. Okay. Now and another thing is something like this Hermitian matrices has a real eigenvalue. So this is will be U something like this D matrix will be something like lambda to lambda n, where lambda I belongs to R. Lambda is real. So now you take this e to the power a. Okay, so you and if you exponentiate, you take e to the power lambda n 0 0 u inverse. Since lambda n belongs to R, this implies e to the power a has positive eigenvalues. So that means, and it is also easy to check that. Let's check that e to the power a belongs to HA. Means now, so that implies e to the power a belongs to PNC because it has positive values and it is Hermitian. So that means exponential map from this sorry, this is a map from HN to PNC. Now for a real matrix, use the fact that for a real matrix, use the fact that that any real any symmetric matrix, any is orthogonally diagonalizable. Now you take A belongs to X belongs to Hn. So you are this implies e to the power x belongs to PNC. So what I will do, I will show that this converse is also true. This is a very important proposition. Okay. So if x belongs to Hn, this implies e to the power x belongs to PNC. I want to show the converse, and this is a well-known result, but I just wanted to prove that because that will be so that you can remember the idea. So let A belongs to PNC, then there exists a unique T belongs to Hn, so that e to the power T is equal to A. Okay. Now, if A, moreover, if A belongs to PNR, then T belongs to then T belongs to Sn. Okay, if A is a real matrix, then you can T is a symmetry matrix. Proof is very simple. Okay, so just idea. Okay, statement. This statement is clear. So okay, so what I'm saying, A is a positive definite matrix, positive definite matrix. Then there exists a unique T belongs to Hn, so the e to the power T is equal to A. So in principle, you can define logarithm function on this positive definite matrix. Okay, so idea is something like this. So idea. So since A belongs to PNC, okay, so A can be diagonalized. A is equal to something like U, some diagonal matrix and U inverse. Now since this is positive definite matrix, so this will get lambda 1, lambda 2, lambda n, where lambda is greater than 0. Now since lambda is greater than 0, I can write lambda I is equal to something like e to the power mu I. Let us replace this. So I will write this e to the power mu 1, e to the power mu 2, e to the power mu n. And what will be your d? What will be your t? If you t define like this, is u mu1, mu2, mu n, u inverse, then you will get that e to the power t is equal to a. Okay, and you need to show that t is unique. Okay, so is this idea is clear, Mithunda? Okay, so
Yeah,
Mithun?
yes. No.
Yes. Okay, good to hear you. Okay, so let us write this proof very clearly. Okay, proof. So this was the idea. So since okay A belongs to PNC, so there exists an orthonormal basis V1, V2, Vn, so that AVI is equal to e to the power mu I ui, where mu I belongs to R. Okay, so this is because the A has positive eigenvalues. So we define T of Vi by mu I Vi, and this is I am defining T on the basis vector because this is a basis thing. So T is well defined, and by this definition, and clearly e to the power T is equal to A. Okay, because okay, so what is e to the power T Vi? Okay, this because or e to the power T Vi is equal to okay, yeah, this is easy actually. Okay, so e to the power mu I Vi, and this is ABI. Okay, so you can check that. So if now if so what I am doing, if suppose U is equal to your V1, V2, Vn, this matrix, because this is an orthogonal matrix, this is an orthogonal basis. This is belongs to really Un, and what I am saying that so what I am saying that in this basis, this so A is equal to your U inverse U e to the power mu 1 into e to the power mu 1 U, and T is equal to U inverse mu 1 into mu n. So these are mu 1, mu 2, mu n. Okay. So by this, since U belongs to UN, check that T belongs to HN. This is clear. You can check that. Now I want to prove uniqueness. Uniqueness is very easy. And
Yeah, Mona, just one question. Can you go back to that previous page? Yeah, so you, please excuse me if I have missed something. So, are you really using that fact that you are taking an orthogonal basis somewhere?
orthonormal basis.
Yeah, have you used that fact somewhere?
No, up to this I have not used here. But after that, if
Hmm.
U is equal to B1, B2, Bn, then this belongs to UN. Okay, I have to show that this T is also belongs to HN, right?
Yes.
If U belongs to B1, B2, Bn, whatever I have written ABI is equal to e to the power mu IBI, that translates to like this: A is equal to U inverse e to the power mu 1, this into U, and I have the TBI is equal to mu IBI. In the matrix part, this actually translates to like the T is equal to U inverse mu 1, mu 2, mu n, U. And from here, you can check that T belongs to HN.
Okay, okay.
Okay, so now this claim this A and T has same eigenvector. Okay, so that will say that precisely I will prove that precisely if AB is equal to e to the power mu v, then TB is equal to mu. Okay. This proof is actually I am running out of time. The proof is proof of the claim. So one fact is easy. If TB is equal to mu v, then clearly this is AB is equal to the power TB. This is equal to e to the power mu. This is easy. This direction is easy. No, this direction. Sorry. This direction is easy. The converse thing I want to do. Okay, converse. Let us use a phrase. Converse thing. Converse. Suppose AB is equal to e to the power mu b. Okay. So B is any vector and B is not equal to 0. You can assume. So B is any vector. So B I can write like this. B is equal to, in terms of I is equal to 1 to n, beta I vi. Okay. So since and I can expand that uniquely because vi is a basis, right? So this is same thing as I can write this beta I not equal to 0, beta I vi. Okay. Now I want to explore this. So AB is equal to e to the power mu b. So A, and I put that beta I not equal to 0, beta I vi is equal to e to the power mu b is equal to beta I not equal to 0, beta I vi. Okay. So beta I not equal to 0, beta I, this is A vi. Okay, beta I not equal to 0, beta I e to the power mu vi. Okay, so now what is A vi? A vi is your e to the power mu I vi. Okay, so if you really, this ABI is equal to the power mu I vi, I am putting that. So this is e to the power mu I vi. This beta I not equal to 0, beta I e to the power mu vi. Now these vi's are basis elements. So I will get beta I e to the power mu I is equal to beta I e to the power mu. Now since beta I not equal to 0, as beta I not equal to 0, I can cancel that. So I will get e to the power mu I is equal to mu. And since mu I and mu belongs to R, so I will get that mu I is equal to mu for which beta I not equal to 0. Okay. Now, so this is clear that mu I is equal to mu. So I get TB, the T is equal to beta I will take just your at most 5 minutes because it's not. We will. Yeah. So just okay. So beta I not equal to 0. Beta I vi. So beta I not equal to 0. Beta I mu I vi. But mu I is your u mu. So I will get beta I not equal to 0. Beta I mu vi. So I can pull out this mu and beta I not equal to 0. Beta I vi. And this is nothing but mu v. Okay. So I am getting Tv is equal to mu v. Okay. So and which was our aim to prove this. Our aim was to prove that Tv is equal to mu. Okay. Is it clear? Manojda, is it clear?
Yeah, yeah.
Okay. So I will just finish the proof uniqueness. Just uniqueness. Suppose there exists some another t tilde belongs to a chain, so that e to the power t tilde is equal to e to the power t tilde is equal to a. Now, as t tilde belongs to a chain, so there exists an orthonormal basis. Here, in this case, you can take any basis W1, W2, Wn, so that e to the power, okay, so that t tilde of Wi is equal to some delta I Wi, where delta I belongs to R. Okay. So suppose there exists another logarithm, another t tilde belongs to a chain, so that e to the power t tilde is equal to a. As t tilde is Hermitian, so there will exist some orthonormal basis W1, W2, Wn, so that t tilde Wi is equal to delta I Wi. This W1, W2, Wn may be different from this V1, this V1, V2, Vn. This V1, V2, Vn, this may be different from this W1, W2, Wn. Okay. So from here, I will get e tilde Wi is equal to e to the Wi. Okay, delta I belongs to R. So that is same thing. E to the power t tilde is equal to a of Wi is equal to e to the power delta I Wi. Okay, delta I. Okay. Now by using our claim, okay, so you will get T of Wi is equal to delta I Wi, and this is nothing but same thing as t tilde delta I. Okay, so t and t tilde agrees on basis better, so t is equal to t tilde. So this proves uniqueness. Now one thing is if A belongs to E and R, then use this fact that orthogonal matrices are use this fact that symmetric matrices are orthogonally diagonalizable. Okay, and then you will get that T belongs to Sn. If okay, so let me write that if A belongs to P and R, so one can show that T belongs to Sn using use the fact that symmetric matrices are orthogonal diagonal. So this is so this finishes this proof of the theorem, and you can also prove that this T depends upon continuously on A. So a remark, just a remark. One can show that T in the previous first proposition depends continuously on A, and I will not prove this thing, and you can see that theory of Lie group Chevalier, this book, it is there, this book. This is not also difficult. So, okay, but it is really little bit lengthy, so therefore I have omitted that. And using this thing, this is the final theorem. You will get that exponential map from some Hn to P and C is a homeomorphism. And you will also show that exponential map from Sn to Pnr is a homeomorphism. Okay, I will stop here. Okay. Okay, proof. Use the remark and previous proposition. Okay, so this is. Okay. So I will stop here.
No, but you need the continuity of the inverse map also, right?
Yeah, that's what I was telling that. This is the basically the continuity of the inverse map. This remark. T is
T in the P. Okay.
Depends continuously on A.
Okay.
Because I didn't include this here because I thought that since I am not giving the proof actually, therefore I didn't include that.
No, but I think it can be shown in other way also, right? These exponential maps are local diffeomorphism, right? From the Lie algebra to the Lie group, so you can use that.
So
also.
as such, use it. This is all about homeomorphism. Okay, so not diffeomorphism from Lie algebra to Lie group. That's okay, but I am not saying that this map is not.
But you need to say so. Are these Lie groups?
So who is this? No.
Yeah. No.
PNC is not Lie group.
Okay. Yeah, then I don't know.
Okay, so I will stop here, and if there are any questions.
I think there are no questions. We will stop. So when do we meet next time? Monday, right?
Monday 3:30 to.
I'll stop recording.
Okay, one thing, sir, I just wanted to say.
Yeah.
If somebody is not able to access the videos or lecture notes, something like that, you should send a mail to Pritham. Actually, he is Pritham. So he is doing that. He's adding it. Okay. So let us stop here.
Yeah. Okay. Thank you.
Chat box.